Hello and welcome. I messed up something doing the recording or streaming, so we will walk through a quick summary right now, and hopefully tomorrow or Tuesday when we pick up, things will make sense. So we started off the day handling error messages for lexical analysis, and that's mostly in the Lexer. So what we've done is we added a message to the errors. So any error has an error message. The places we really were messed up was here. So um, if you get an error back, we want to check that you got any error you got back. We're just going to return that instead. So this nestable comment, if your comment didn't close properly, you get an error. We return that. Otherwise, it's treated like a space and just ignored. And basically, the changes we made were around this. So the token error took a message argument. We made sure all the right ones had the right value for this. So here's the unclosed comment, your nestable comment, brace dash. If you get in there, brace dash, and you don't close it, you just have an end of file, you trigger this error and it returns that value, and then the top level thing checks it. The other errors, I think we had them working as of last time. We did add this one, unexpected character. So let me pull up the tests. All right. So basically, any of these tests that had the error here. So here's an accented E French character, well, whatever language, I guess, any language that has that. We catch unexpected error because it's not a legal character for what we're doing in Elm, as far as I know. Maybe in strings. And same thing here, float needs digits after decimal. So we're just augmenting them. All right. The second piece of that is the location. So line number and column number. And I think you probably noticed they were there. Let's go back to the tests. So here location is 1, 3, line 1, because we're starting here, and location 3, we were here at the end when we expected to see some more digits. And similarly here, everybody's kind of pointing just after it is where they notice things go wrong. Okay, that's all pretty simple. We put it in the input side. It really was a decision. Are we going to handle this on the input stream, or are we going to handle it on the parsing, the lexical analysis stream? I don't know. I go back and forth, but in the end, I decided to do it here on input. We define a new location type, just the line number and column. It's a struct. It's just going to hold those values. And we gave you a way to find it. So you just call the input.location, and it constructs a location object for the current position. And then down here we're updating. So normally you just work your way through an array and update current this index. Now we have a column index, and if your character was a new line, we update the line number, add 1, and reset the column. All right. It's not. I mean, it's not pretty to have it down here, but it's not that horrible either. So I don't know. I'm not sure what I'm fighting against there. All right. But basically, everywhere we catch an error, my Lexer go, we pull out input.location and pass that along with it. So um, you might wish you knew where every token was located, but I think for purposes where we are now, we're just going to keep track of the error locations. All right, so that was the first two things. Refactoring, should my input handle token or leave it in the Lexer? We just decided to leave it in the Lexer. So input, well, let's see in the Lexer first, I guess. We have a token, which is a array of characters. And if anybody ever needs to use it, like uppercase name down here or number, digits gathered into token, and then at the end return a string, convert it to string of token, and so on. That's one place we could do it. Let's see the input. Yeah, here's input. Another alternative would have been some sort of thing to say start collecting and then finish collecting, and what's the string I got, and we could have put it up here too. I don't think it's a big difference. It it would probably be slightly more efficient to gather it here, but I don't think it's going to matter on the C on a PDP-11 might matter. I don't think it's going to matter quite so much on a multi-gigahertz laptop. All right, and then what else are we doing? All right, and then finally we started in on a new definition. So you want to say x equals 3 or square root n equals n squared. Okay, that's going to be a new kind of definition. So let's find our parser. Well, let's find Lexical because we did a slight. We added an equals operator here. So you match on an equals, you get it, and you return token equals. And then where's parser? Here's definition. Name equals expression. Eventually it'll have arguments, but we don't have them yet. But you get a lowercase name, match the equals, match the expression, and return this definition object that has it. Okay, and let's take a look at definition. So definition is really just kind of mostly a data bag. It's holding a name and expression, and it takes the type from the expression. That's not clear that's the way to go, but I think it may be. And then it also does equality tests. So if you say definition of x equals 3, definition y equals 3, we want to say those are different. More for testing purposes than usage, real usage. Normally you just get what you're given and evaluate it. All right, and then we discussed, and this is where I'm not as clear on what's going on and how to do it right. Somewhere we have to keep track of these names and the symbol table or context that they go with. And really, with languages like this, and many programming languages, you have sort of a nested context because you have different scopes, and you have to build a sort of tree structure that handles their nesting. We're not doing that yet. That's kind of where we just left off. But here I'm coming in, I'm going to say there's a Boolean type that has values false and true. And there's a top level thing where the top level definitions from your file come in. So if I start off, I'm empty, and I say x equals 3, well, now my top is x equals 3, some sort of definition of the expression, and point to the system otherwise. So when you want to find a value, let's say false, I'm going to first look in my context with x3, the top, and then failing to find it there, I'll look in the context of system. And if you go to line 37, square root n equals n squared, now I have top is square root n equals n squared, but there's also a context for the square root, the right-hand side, and it's got a parameter n, and otherwise it goes to top. So if we're looking for a value, let's take the next one down, foo n equals n plus x. The top level is foo n equals n plus x, square root n equals n squared, and x is 3, or go to the system table. The square root context is n goes to top, a parameter n, and then go to top. The foo context is also a parameter n and goes to top. So if you're looking to evaluate n plus x, you're going to look first in foo context, then in top, for n and for x. You'll find x in the top level context. We'll never look in the square root context because that's irrelevant to us. That's a totally different n. Somehow we'll have to build a nested symbol table that reflects all this, and figure out how to do that. And so we had this discussion around in parsing. You have this notion of synthesized attributes and inherited attributes. So synthesized means built from the bottom up. And an example of that is the if statement here. The if statement takes a condition, it takes a condition expression, it takes a left-hand expression and a right-hand expression because it's if, condition, then left, else right. So the three, the three expressions are the big thing out of that. All right. So we build up an if expression, condition left or right, and we compute the result type that this thing has. Okay. And that's all information coming from stuff from our children. We call them, take the results of what they give us, build a new result and return it. And that's the return value expression here. The inherited side is more when you get into symbol tables, and it's not clear to me if we should push this down through the parser or the interpreter or both. I guess we have to push it through the interpreter, but we probably need to build some sort of a symbol table for the parser too. And if you did, that would go the other way. It would be something that it would be a symbol table of some sort sitting around up here, and then we would pass it into parse and pass from there into expression and into, if statement and everything else. Everybody would get this symbol table floating in down. They might need to adjust it, which has its own challenges, but one way or the other, we're trying to put information in the symbol table, so it's got to come back from the bottom too. But the real thing is we're passing it down. So then once we get to the next expression or definition or whatever, they can put things in the symbol table or look them up there too. The interpreter definitely has to have it because it's going to look things up and evaluate expressions in a context and so on. All right, so let's see where we left off. So, so we defined this test, definition tests. No, we defined the class, but didn't define any tests. Okay. And with the test we're going to write is something like x equals 3. And what are we going to check? Well, there's nothing you can check. I mean, you can only check that the symbol table has x in it. Defining the symbol table is going to be a fair bit of work, but we'll do something simple to get started. What we did instead, let me adjust slightly. What we did instead, we found that the interpreter tests, let me diff this. We had lots of tests in there on the left, the original. And this is from when the interpreter had all the case statements, had a big case statement for the node types. Last time we changed the node types to class structure. We still had these tests that were checking the interpretation, but most of them were doing things more to, like we were verifying that 739 gets interpreted as 739 is a number. So we read it, we pass it in, we parse, we get a tree back, an expression, we evaluate the expression, and then we print the expression, and that's what we expect. So it's checking that the interpreter plus, the read is the parse, but it checks the evaluate print part of the REPL. And we just need one or two test cases is enough for that. So here we've left this one in. If true, then 3, else 2. Expects 3.number, 3 of number, and it won't get that unless it actually does evaluate and print. All right. And so what we did instead then was we pulled those examples and pulled them over into the classes for the individual nodes. So we've got the as string tests on that one, same thing on float, same thing on custom value, bool false. Well, this is really, would be more accurate to call this as string for Boolean false, something like that. Okay, custom value, and then if expression has a more complicated situation. We're going to check, did you calculate, well, I don't know, maybe this is not even useful. So we're checking that the if expression has the right types, but we don't need to know that here. That was done by the parser. Okay, so I'm going to leave a little note here for us next time. Do we need these? Done by parser. The real thing is the type comes from whatever got set up in the when the if expression got created. So the parser judged int plus float. If one side's an int, the other side's a float, the result should be a float no matter what. And that type comes from the parameter. So there's no thinking involved. We don't need to test three ways. We do need to make sure that the parser enforces these rules, and check for tests there. Okay. And given that this passed, I'm going to just break it. All right. And then, yeah. So I think that gets us through it. I mean, this is the real challenge we're going to have next time. All right. And I think that'll be enough to get us going on which tests we're going to look at. Yeah, I think that'll be a good place to stop. I don't know. Maybe I should just do it now and be done with it. Let's do that. Take a few more minutes here. All right. So turn this off, and let's look at these if expression tests. Okay. So, let's find the parser tests. Test if. Okay. 2 integers has type number. 2 types has type error. I don't think we've got a very good example here. Number. Yeah, I think we want to pull these tests over here. Let me lock this one in. Where's the if expression tests? Okay. Let's pull these two. Okay, I guess we were just debating last should the interpret. So mostly we do interpret and we get a value. This is uninterpreted, but maybe we want to look at it. So we thought, oh, let's give it an as string. So I think we'll leave that as a failing test. But let's get these tests over into the parser tests. Okay. So evaluate if when true, int plus int returns number. Type int plus int. Okay. Type int plus float returns float. No, well, I just put them back where I had them. Okay, can't be trusted. All right. Type. How about type comes from saved type? All right. So if I did float, let's make one of these a float. A float value 3.5. Elm-type.float. It should be coming from here, like that. Good, and let's find those parser tests. Test if. Well, that's reasonable. So check successful parse. I don't know where that came from. If true, then 3, else 2.5. Okay, and what we expect to get back is an if expression with bool type, that, and float. Bool type, okay, we'll copy, I think, I don't know. At some point it'll be a system type and I think we'll have a better way of going with it. Okay, but for now, we'll just make that name. And then bool type, float. This is assert equal values. Well, I don't have to do that. Okay. Expression and close the whole thing. Okay, and then I think we'll borrow this. Okay. This one is if false, then 3.5 else 2. Let's do that. False 3.5 is a float value. Elm type dot float. Elm type dot number. Elm type dot float. So if false, then 3.5 else 2, result type float, even though one is an integer. And this is float plus int. This is int plus float. All right. That seems good. Oh, but it's not. Interpret. Oh, that's over. Okay. Let's commit this. Move tests from interpreter tests to the individual classes. Move if type calculation test to parser tests. Okay. That's good. I think we will leave this failing so we know what we're doing there. And I want to put a failing test in our definitions. Test 2. Down here. Okay. Well, we didn't do anything there. I think we'll pick up there. That should be fine. We got it in our to-do. Move tests from interpreter test to individual classes. Okay. And interpreter with symbol, table, or context. Okay. I think that'll be what we need for next time. And we'll pick up there. I don't know. The symbol table, that's a tricky one. We'll have to tread carefully. All right. Well, I apologize again for messing up the recording, but hopefully this summary is helpful. See you next time.